Hello and welcome back everyone in the series of data science using Python. In this video, we will learn about dimension reduction. First, demonstrate how you will identify multicollinearity by Python or R language. Multicollinearity occurs when two or more predictor variables in a regression model are highly correlated. This can inflate the variance of coefficient estimates, making it difficult to determine the individual effect of each predictor. What are the symptoms of multicollinearity? Large changes in coefficients when adding or removing predictors, non-significant coefficients despite a high R score, R square value, high variance inflation factor VIF or condition indices. Methods to identify multicollinearity in Python. Correlation matrix. Correlation matrix helps to identify pairwise correlations between predictors if the correlation coefficient between two variables is high. Example, between zero point 0.7 to minus zero point 0.7. Collinearity might be present. Second, variance inflation factor, VIF. VIF quantifies how much the variance of a regression coefficient is inflated during due to multicollinearity. Eigenvalues and condition index. Small eigenvalues in the correlation matrix indicates multicollinearity. The condition index ratio of the largest eigenvalue to the smallest can also signal multicollinearity if greater than 30. So let's understand this with a code example. Here is the code. First, we will import all the necessary libraries like pandas, numpy, skill-learned datasets, state models tools. Step 1. Load a dataset using the diabetes datasets as an example. Step 2. Check correlation matrix. A high correlation between predictors indicates potential multicollinearity. Step 3. Calculate variance inflation factor VIF. Add a constant to the dataset. Calculate Calculate VIF for each feature. Display VIF values. Interpretation. Let's run this code and see the output. Here is the output. We have got the correlation matrix for age, sex, BMI, BP, S1, S2, S3, S4, S5, and S6. And variance inflation factor VIF for all these factor features. So let's move to the another topic. And here is the another topic, which is how you will apply principal components analysis using Python or R language. Principal components analysis (PCA) is a dimensionality reduction technique that transforms a dataset with potentially correlated features into a set of linearly correlated components called principal components. Each principal component is a linear combination of the original variables capturing the maximum variance in the dataset in the data. There are These are the few steps in PCA. Standardize the data. PCA is sensitive to the scale of data. So standardization means mean is equals to 0 and variance is equals to 1 is typically required. Second, compute the covariance matrix. Measure the variance and correlation between the feature. Third, compute eigenvalues and eigenvectors. Eigenvalues indicates the amount of variance explained by each principal component. Eigenvectors define the direction of the principal components. Fourth, select principal components. Choose the components that explain most of the variance. Cumulative explained variance threshold. Example 95%. Fifth, transform the data. Project the original data onto the selected principal components. Let's understand this with an example. Here is the code. First, import the libraries. Step 1, standardize the data. PCA requires the data to be standardized. Step 2, apply PCA. Initialize PCA to retain all components. Step 3, explain variance ratio. Plot explained variance like figure, bar, step, X label, Y label, title, legend, show. Step 4, reduce dimensions. Retain only the components explaining 95% of the variance. Then print the X scaled shape and X reduced shape. So let's run this code and see the final output. Here is the final output, which has explained variance by principal components. Principal component and explained variance ratio. Original data dimensions are 442 on the x-axis and 10 on the y-axis. And reduced data dimensions are 442 on the x-axis and 8 on the y-axis. So that's it for this lecture. We will meet in the another lecture. Okay, thank you.